Welcome to week 2, right? We've got, I would say, the review part behind us, and we're ready to charge ahead with some real machine learning, except nobody thinks of it as machine learning. Today we're going to talk about regression, ordinary least squares. But the thing is that it really is machine learning, people. Like, I can point you at any number of large neural networks where their final output layer is really just a regression, okay? So it still gets used. And more to the point, this is your first deep dive into the math in a way where, we're setting you up with skills that are going to be useful to you in the future when you're trying to understand those deep neural networks, okay? So just a reminder, this is our week ahead. We have assignment 1 due on Wednesday. Does anybody have any problems, issues, questions on assignment 1 in the next minute? You've all already done it and turned it in? Nobody's going to last minute it? I'm joking. I know you're going to last minute it. Okay. So I do want to just pull out there, I did have one student find some issues with a markdown, at least in one of those cells. So if anybody finds any other issues with the assignment, please let me know, just so I can update for future quarters. Okay. Then let's do some math. Frag. I should have changed this thing. We're not doing lecture participation survey anymore this quarter. And these things are all wrong. So I guess I should have paid attention to my slides, huh? So you may have already seen that in the pre-lecture, what I was doing was I was looking at Numpy, okay? Because Numpy is like this basic way to do vectors and matrices, and everything in machine learning is linear algebra. So if you're not Numpy happy, please actually go play with this notebook, because listening to me is a bad way to learn to use software, okay? So play with the notebook, get comfortable indexing and creating matrices and arrays, okay? Make sure you can do that. Okay, so just a reminder, we were talking about convexity at the end of last time, right? Convex functions are awesome. Why? Why are convex functions awesome? Who wants to tell me? Yeah. You got it. There is one and only one solution to a convex function, right? And that means if there's one and only one solution, if you're lucky, you can probably solve for it analytically, right? So here's the deal. If we have a strictly convex function, we've just got to look for the place where the partial of the function with respect to the weights, because the weights are what control what the loss is, right? Find that place where it's equal to 0. Solve that equation, and you're golden. You've got a one-stop, we can do the answer. Well, guess what regression using ordinary least squares is? It's convex loss surface. So we can solve it in one go. And that's what we're going to do today. Before I go all the way to that, I do want to remind you of the definition of convexity. There is a mathematical definition, right? And the way it works is we can pick any 2 points anywhere. We can draw a line between them. And if that line is above wherever the corresponding point is on the actual curve, then it's a convex function. If the line is on the curve, that's a convex function, but it's not strictly convex. So anything that's got a linear component in it, like this bilinear V, right? It's two lines stuck together in a V. Anything that's got a line in it, it's convex, but it's not strictly convex. Strictly convex, then this line is always over the curve. Here it can be over or equal to. Okay? And anytime we can draw a line between 2 points where the curve goes over the line, it's not convex. Is a concave function convex? Yeah? You got it, right? A concave function has exactly the same guarantees to be able to find an analytic solution. All we've got to do is just do minus this concave, and we get a convex. You got it. So concave functions are actually convex functions. This is the problem. Only that situation is our real worry. Any questions on convexity? Okay. So in reality, we often have the situation where we have non-convex functions, but they're differentiable. We follow them through gradient descent. I think I did all this last time, right? Am I forgetting? We didn't do this? Somebody tell me. Yes? No. Okay, then I'll slow down. I vaguely felt like I did this, but all right. So if it's differentiable but non-convex, like just throw out, for example, every single deep neural network ever, okay? These are non-convex loss surfaces in these complicated neural networks, but they're differentiable. So that differentiable bit tells us that we can't solve in one, but we can move towards a locally optimal solution. Okay? How do we move towards a locally optimal solution? Well, wherever we're at, all we've got to do is start there. Let me do this the right way. We calculate the gradient. The gradient is the first derivative with respect to W. Okay? By definition, that gradient points uphill. Okay? So instead of doing this and doing the gradient, what I want to do is I want to follow the negative gradient, which by definition points downhill. And I just take a step downhill. Okay, so the derivative of this big old nasty matrix thing, whatever the loss function is, it's gradient, negative gradient going downhill. That's what we want. We take a step in that direction, we're rolling downhill. Okay, you can also do this for convex functions, but no need, because again, we can solve it analytically. We can get the answer in one. But yeah, you can use gradient descent on a convex function. It's just that people tend not to. Okay? But hey, all we got to do is set that partial equal to 0, and we get that closed form. One shot, no iteration. Okay, so if it's convex, find the derivative. You got to get the derivative. So that means you got to start with the loss function. That's known. You've got to do calculus to get the derivative of the loss function with respect to W. That's an equation. Set that equation equal to 0, solve. All good? Okay. So to solve for the argmin of some arbitrary loss function, let's say it's this one, this function is power of 2. That means it's quadratic. What shape is a quadratic function? Parabola, like this. right? What you can kind of vaguely know if you're thinking geometrically is that this must be 3, because W minus 3 right there. Okay? Wait, did I do that wrong? Is it 4? No, it's 3. The 4 shifts it upwards. Good job, Jason. Okay. Yeah, all right, so that's a parabola defined there. Let's do this. Okay? So the derivative of a squared function is 2 times the thing, right? So this part goes away, goes over there. This goes down to the first power here. I'm sorry, I'm going to undo that. That was some really bad notation, right? That's now from the second power to the first power, if you remember your basic calc. This guy is a constant with respect to W, so it just goes away. Okay, so set that equation equal to 0. Solve. W equals 3. Right? Like promised. So it's really easy math, really, but the vectors and matrices make it look more scary. Okay, shall we apply it? So let's start with a little history lesson before we get into the math. Regression, why does it even have this name? It's because of an old white dude who was not very nice, named Sir Francis Galton. So Galton is actually a really impressive mathematician in the end of the 19th, beginning of the 20th century. And he was probably just some sort of OCD freak who went around and counted everything, right? So the famous story, probably heard me tell it in Cogs 108, where the wisdom of the crowds. He was at some sort of fair, and he noticed the situation where, people have to guess the weight of the prize bull, because, this is like 1900s in England, right? And it turns out that if you took the average of all the guesses from all the people at the fair, it was more accurate than any one person's guess, right? The average among a crowd, the mean of the answer was the right one. And he also applied the same thinking in his interests in racial purity, right? So he always argued that, yes, you can have the occasional person of color, although he wouldn't have used those words, who is very smart, but on average, because white people are better, according to Francis Galton, right, then you would, among the group, see a regression to the mean. When you take the average across a group, you get a different thing that you can tell between white people and non-white people in Galton's world. Or he also applied it to children, right? So sometimes you get a really tall child compared to the parents, but on average, children regress to the mean of their two parents in terms of their height. So this terminology, regression to the mean, which generally is a pretty negative connotation, especially when used in a racist's mouth, is where we get the term regression. And regression is indeed this same idea, the idea that there is an average truth, and that truth is changed by random noise, okay? So when you make measurements, what you're measuring is a true relationship. On average, the height of the parents is going to determine the height of the child, to use something he wasn't wrong on, okay? Right? On average, the height of the children will be determined by the height of the parents. There's a real relationship there. But individual people vary. So some children are taller or shorter than their parents' average. So, if you've seen a Kincucks or a pachinko machine or stuff like that, you've seen the idea, right? There's a stochastic process when a bean comes in here and it goes wherever it goes, right? It could end up out here on the outside of the distribution, but on average, the path of the bean through the quincux is going to be towards the mean. So machine learning is statistics. In the end, we are using the same assumptions you're used to from your stats class. The idea is that there's a true population out there, and inside that population is a real relationship between X variables and Y. We've got a noisy sample, and in that sample, random events happen, and we don't have an accurate picture of the distribution of the sample, but on average, it does expose the relationship we're interested in figuring out. So when you apply that to regression, this is the intuition I want you to think of. For every little chunk of X, we expect measurements to be noisy around this mean. Okay? And there'll be a noisy set of measurements around this mean, and so on. And what regression to the mean is trying to capture is that average line, right? Where the most likely answers are going to lie when we get noisy measurements. So this is kind of the math, right? The idea is that there is a real deterministic relationship. There's an output, which is a function of x's and w's, that's noised up by some random Gaussian noise, epsilon. And so our observations, y's, they're noisy measurements of a true relationship. Okay, does anybody have any questions at this point? The idea is that on average, the noise cancels out and we can measure the truth. But that depends on what? Getting to the truth depends on what? What are our assumptions? Anybody? One is the classic statistical problem we always have. Does that give you a hint? It's population size. Sorry, who said that? Yeah. So you're right? Like if you don't have enough sample, you're going to get potentially really bad estimate. Okay? Training size matters, right? Okay. If you would like a chance to play and see how OLS works, I always recommend this lovely live, thing that you can click on from satosa.io. You can drag these little things around and watch how it changes the line of regression. It's a wonderful exercise. I'm not going to do it in class. You should play with it. What I'm going to do now is let's play mathematician and pretend that I know how to derive stuff. Okay? I've got something to make sure I don't mess up. But let's see how well I can do without it. So we start from this idea. We have data points that are noisy versions of some truth, and we want to fit a line of regression to them. Okay? This line of regression is denoted as y. We've got some data points, x1, x2. I'm going to make that more of a point, x3. Okay, all these points. Now, we need these things in here. And I want you to note that these lines I'm drawing, these distances are called residuals. Okay? Our residuals, they're E. So we've got E1, E2, E3, and so on and so forth. Here's the trick mathematically. The best possible line of regression using ordinary least squares is the one that minimizes the sum of squares of those residuals. Okay, I think we can intuitively get the sum part, right? Intuitively, you just add up all those errors, and that's your total error. I think that works. Why square? Why are we squaring each one of those e's? Right. So this x3 is just as much of an error as x2. If we did just the e, that e is a negative e, and it would cancel x2. We don't want it to cancel. We want to get, that's more error. E3 is more error, not less error. We don't want it to cancel out E2's error. Okay? So we've got a couple of ways to do that. You could just take an absolute value. That is a different loss function, and it is a valid loss function. Okay? You can do what's called L1 regression. Guess what we're going to cover on Wednesday? But not yet. We're going to do L2 regression, or ordinary least squares, where we square the term. And that square means that single outlier errors, their error, I don't know, call that e to the n, that error gets squared. Big errors get really big. So single outliers have a lot of force in determining the line of regression with ordinary least squares because we square the error term. If that was an absolute value instead of a square, that single outlier doesn't have as much lever arm to move the line of regression. Does that make sense as a concept? We're going to cover it again on Wednesday, so no worries. All right. So we care about the errors squared. Let's just do a little bit of notation quick before I get into the errors. We've got x's. So I'm going to call this x to the n as a vector. Remember, we're doing column vectors. So I don't know, how many variables do we have going in? In general, it doesn't matter. We can regress on one variable, which is what I've drawn here. The line of regression is a single x, right? But you can just, in your mind, turn this into regressing on 4 variables, right? Like housing price, number of bedrooms, blah, 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 right? Has wings, lays eggs, right? Any of our things, we just put all the variables in and we regress on them. Okay. I do want to make one big note here. See this x of 0? So I'm going to say if we have n variables, like if there's 4 variables, we have x1 through xn. What's this x0? I want to enforce the existence of a y-intercept. I want to add the b term in y equals mx plus b. But I want to do it all in one step with our math. So this x0 is always just 1. So I have n variables plus the single number 1 at the very beginning. That single number is a constant term. And when that constant term gets multiplied by our w vector, that produces the bias, the b term, the y-intercept term. Okay? We're going to cover this again in a minute, but I just want you to keep that in your mind. In this notation, we always have to have an x of 0, a bias term. Okay, so here is the magic. Residual sum of squares. Well, if we have, just like this, e of n, right? So e of n is some number. What is that number? That's going to be the truth. Sorry. I need to make a small notation change. Dummy. This is y sub 1. This is y sub 2. Right? So the error is going to be the truth, the y value of the data point, minus our estimated line of regression answer, right? This is y hat of 1. That is a hat. Means an estimate. Remember that notation? Hats are estimates. Okay, so that difference is our vertical distance between the true data point and the line of regression Well, I can just write that like this in matrix land. Okay? Actually, let me do this with better notation. So E sub n is a single error. I'm going to define an error vector. Okay? This is my attempt to write a boldface. So this error vector, E1, E2, dot, dot, dot. So if we have n data points, we have, and I should keep some things straight. Let's use k for variables and n for data points. My bad, I apologize. Okay, so this E vector is all the errors of the entire training data set. Are we good with that transformation? We've gone from over here, from a single data point, to here, this being the entire data set. All right, let's go again. So now I'm just gonna write as if everything's vectors, right? E is this vector, that's a column vector. X, okay, is now, let me maintain notation. X is our design matrix. And what that is that's vector x1, vector x2, vector x3. Notice they're all transposed because what we're going to get is a column of ones, right? All the way down to x of n, comma 0. And we're going to get a vector of, x of first, second row, second data point, first column, and so on and so forth, all the way down to the nth data point, first column. And this will be the kth column, all the way down to the nth data point, kth column. That's our entire training set. The variables are columns. The data points are rows. Right? We're all good on that? We've done it a couple of times now in class. Our weights vector is also going to be a column vector. Right? Where this is, up to w sub k, because weights are going to be on variables, right? We're regressing on variables, so it's k long. This is n long, because errors are data points, right? All right, we're almost there. You ready to go? So, the residual sum of squares is going to be E transpose E. Okay, E is a column vector, so E transpose is a row vector. A row vector times a column vector. Rows, number of rows, 1. Number of columns, 1. Means the output is a scalar, right? Effectively, right, when you do this math, it's E1 times E1 plus E2 times E2, right? Because E1 here, E2 here, E1 here, E2 here, right? Just basic linear algebra. That is indeed the residual squared and summed up, the residual sum of squares, right? That's why its name looks like that. This is our loss function. Okay. Well, remember what E is? Just a reminder, E is equal to y minus y hat, which is the same as saying y times x, our data points, multiplied by w. Our job is to find the w that makes loss smallest. So we plug this into that. Okay, I'm going to stop for a second, let people catch up on their note-taking. Just also a reminder that this is on podcasts. Questions? Worries? Need for coffee? Okay. All right, let's do this thing. So, remember that this is transpose times the thing itself, where inside it, it's hopefully you remember your high school algebra, how to do first order, inner, last. That's what we're going to do right now. Just in case you lost track, this is E transpose E. Okay, I'm going to undo that because I made life really messy with that. Okay, just a note, right? You really got to make sure you got the transpose on the first one. If you do the transpose on the second one instead, that's something else, okay? So, common mistake, getting the transpose on the wrong one. So here we go. First, so y transpose y. That's easy. Okay. Outer, so y transpose xw. Inner. Okay, so now we get a little tricky. XW transpose, just a reminder, XW transpose is actually W transpose X transpose. When you transpose stuff, you got to switch orders. Okay? So this is minus W transpose X transpose, that's this bit, times y, right? And then the last bit is, again, we got to, once again, switch the orders here. W transpose X transpose. I'm running out of space. I'm going to do it down below because I'll just make this miserable for everybody. W transpose X transpose, and then multiplied by this, which is XW. It's not too bad. Yeah, is there a question? Oh, thank you. Yes. Minus times a minus is a plus, even in matrix algebra. Okay, not too shabby. Let's get it the rest of the way home. So it turns out these are actually the same term, because we can transpose something and switch order. So just to remind myself which version of this is the better one for our notation. We want the W transpose X transpose version. So we want this version for both of them. Well, all we've got to do is transpose this and switch the order, and it goes W transpose X transpose Y, which is W transpose X transpose Y. So this is actually minus 2 times this. these two terms together. It's minus 2 times this. Right? We all good with that? All right. So y transpose y minus 2 w transpose x transpose y plus w transpose, wow, that was bad, x transpose x w. Which one's the squared term? Because I guarantee you this is a quadratic. First, second, or third? I got one person giving me the fingers that are correct. Anybody else? Yeah? The third term, right? The third term is w squared. See this? Let me do that with the highlights. W. This is w squared. It's just got this order crap because linear algebra, right? You've got to have the things in this order to get this down to a scalar. Remember, the output of this is a scalar. It's the total error. So this ordering, w transpose xw, is what gets you down to a single scalar number. But it's fundamentally, it's w squared. All right, so this is a w squared term. This is a w to the first power term. This is a constant with respect to w. Okay, you ready? Because what we need is we need to derive this loss function. We need to get the derivative with respect to w. We need to do and set it equal to 0. That's our next step. Okay, so just a reminder. I guess I better just write it out. So y transpose y, no, not plus, don't do that, Jason, minus 2 x transpose, nope, dummy, w transpose x transpose y minus, no, not minus, plus w transpose x w. So let's derive this. Well, derivative with respect to w. This is constant with respect to w, so that goes away. This is a first order term, so that is fairly simple. That's minus 2x transpose y. This is a second order term, so we know that we're going to be left with one of these w's at the end. The question is which one? The answer is we're going to be left with this one in the back. This is the one that's going to go away with the derivative. Okay? So plus x transpose x w. Well, we need to set that equal to 0. Okay? We're looking to solve for w. We want to get w all on its own. So I'll just rewrite that like this. xtxw equals 2xty. Everybody good with basic algebra? I'll give you a second just to catch. All I did was I moved this over to that side, right? Okay, we want to solve for w. We need to get rid of this. We need to move this to the other side. How do we do that in matrix land? We construct the inverse of a matrix. By definition, the inverse of a matrix multiplied by the matrix is the identity matrix. It's diagonal ones which is the equivalent of 1 in matrix land, right? So this is like just a little aside. If I'm going to call just to keep from stepping on my notation, I'm going to call this matrix M. Equals the identity matrix. Okay? So I'm going to set M to be this thing in here. So what we're going to do is X transpose X inverse times X transpose X W equals 2. Got to keep our order the same. If you don't keep your order the same, this falls apart. Okay? Yeah? Oh, thank you. You're right. That was not going to work. Yeah. This was a squared term right here. Should have been that 2, which means that there was a 2 here and a 2 here, which is now how this works out. Thank you for catching my error. Because things start to cancel out. This 2 and that 2. This inverse and that, because that's an inverse times the thing. And we're left with W equals X transpose X inverse X transpose Y. This is, I'll often use the notation in my slides because I inherited it from the guy who used to teach this class, W star. This is the optimal set of weights, right? This is the set of weights that puts us at the bottom of that convex loss function. Yeah. The W transpose, so can you tell me?
In the second step on the current slide.
In the second step.
You got rid of the W transpose in each term, like from the one before.
From before.
No, if you, same slide that we were on before.
Here, you want to?
Like there's a W transpose in the first term, and then none of them are here anymore.
Okay, so here. And then they're gone at this point.
Yeah.
Okay, because we are deriving, right? So, so this guy, that's W to the first power. What's the derivative of something?
Yeah, but so I'm confused why you are doing this to W transpose instead of like just the normal W's.
Why this one disappears and not that one?
Because I thought we were taking it with respect to W and not with respect to
right,
W
right.
transpose.
So W transpose and W, there's the same variable. They're just transposed. This ordering right here is purely to make this whole thing, this whole term become scalar. So when we do a derivative, we need to get something which is no longer a scalar, but a vector, the same size as the weights themselves. So the reason why this one derives out is because this form gets us a W column vector size thing.
Okay.
It's linear algebra just to make the things work right in shape. If you talk to a real mathematician, not me, they'd probably give you a better answer than that one. But the one I'm saying, the reason why this guy is the one that derives out is because this gives us a W column vector shape.
Okay, thank you.
But yeah, you should totally talk to a real mathematician and find out the answer for me. That's more theoretical. Okay, this is ordinary least squares right here. This is the ordinary least squares solution. Now, some critical elements. You've never had to deal, you've used regression so many times already, I'm sure in COGS 108, you've certainly used ordinary least squares regression, but now you see the math. And suddenly some things start to make sense maybe. So this kind of a matrix inverse only exists for full rank square matrices. So what does full rank mean? Full rank means that none of the rows or none of the columns can be rewritten as a linear combination of other rows and columns. Do you remember in COGS 108 we talked about multicollinearity? If one of the variables is a linear combination of the other variables, like for instance, if those two variables have a correlation coefficient of like 0.97 or something like that, then maybe this is no longer a full rank matrix because you could make up one of those columns out of a linear combination of other columns. When you do that, this does not exist mathematically. And that's why stats models complains vociferously to you that the condition number is terrible when you feed it in data sets where one of the variables is highly correlated with some other variables in the data set. Because just like the solver doesn't know what to do here, it gets lots of errors. Okay. So, ordinary least squares has a set of assumptions that are called the Gauss-Markov assumptions. I used the same slide, but without calling it Gauss-Markov in COGS 108. Right? We're assuming that this is linear in the parameters. It's linear with respect to W. We're assuming this kind of random distribution of noisy measurements around a truth. We're assuming that the mean is going to be 0. We're assuming no multicollinearity. We're assuming that there's no homoscedasticity. That is, the standard deviation at this point in the x-axis is the same as the standard deviation at this point in the x-axis. Okay? If it gets more variable towards one end of the x-axis, if the residual plot, that is, this is x's and this is e's. So if the residual plot looks like this, where it's getting bigger or smaller towards one end of the residual plot, that's heteroscedasticity. That means your variance is changing for different x's, right? No good. Stuff doesn't, the math that we just went through starts to fall down. Okay. And Anscombe's quartet, like we talked about in COGS 108, is also an example of when these assumptions fail. Okay? These 4 data sets look very different, but they have the same line of regression as well as the same mean in x and y and the same standard deviation in x and y. And the reason they have that is because they violate the assumptions, the Gauss-Markov assumptions, and so the math is no longer singular. There's no longer only one answer. Okay. Before you run away, this is my favorite mind-blowing moment. If you were asked to draw an imaginary line of regression through this data, most people would draw something like that. That is not what ordinary least squares does. Ordinary least squares ends up drawing this line roughly instead. Why? Because it only cares about vertical error. Okay? To draw the black line, you need to care about this kind of error. Ordinary least squares assumes measurements in x have no noise. It assumes noise in y, but it assumes noiseless x. Ordinary least squares is not the only game in town, even though that's what you've always used so far for regression. The black line is made by something called total least squares. Okay? Different loss function. All right. Just to let you know, there is a notebook that's already out that you can play with on linear regression. We're going to do it on Wednesday. And if you're wondering, this is the notebook right here. You can click on it already. I have 2 cats. One is Mercury.